Testing. Testing. Testing, 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 testing. All right. Make sure that the audio is working fine. Okay, the audio is working. All right. Welcome to another Hoopo stream here. Hope you guys are enjoying the updated thumbnails and banners. We've been using some AI art generators to step up the branding and marketing for the channel. Today we're going to be looking at a paper called Zero Shot Image-to-Image Translation. This is relatively recent work, February 2023. And the main groups here are Adobe Research of the famous Adobe Products Suite and Carnegie Mellon University, my alma mater. So this is a image, I think it's a diffusion model. Here we go. We propose Pix-to-Pix 0, a diffusion-based image-to-image translation method that allows users to specify the edit direction on the fly. It's diffusion-based. We perform various translation tasks on both real top two rows and synthetic images while preserving the structure of the input image. Our method requires neither manual text prompting for each input nor costly fine-tuning. So, no fine-tuning, which is good. And the lack of fine-tuning is what is meant by zero shot here. So zero shot means you're taking a model which is trained and then applying it directly to some new task without any additional fine-tuning. And image-to-image just refers to the modalities of the input and the output. In this case, the input modality is an image and the output modality is also an image. So that's where zero shot image-to-image comes from. Let's get started here. Abstract. Large-scale text-to-image generative models have shown their remarkable ability to synthesize diverse and high-quality images. However, it is still challenging to directly apply these models for editing real images for two reasons. Okay, let's see what they say. It's hard for users to come up with a perfect text prompt that accurately describes every visual detail in the input image. Yeah, there's kind of a new field of prompt engineering, which is the art or science, if you will, of figuring out what words to type into these text-to-image generators in order for your particular image to be generated. And it's not necessarily a super easy skill, and a lot of times being very verbose is the way that people have found to be good at prompting, but it's hard, as they say here. It's hard for users to come up with a perfect text prompt. While existing models can introduce desirable changes, they often dramatically alter the input content and introduce unexpected changes in unwanted regions. Yeah, I would say this is kind of the main negative with these models, especially if you guys have ever seen videos where people will take every frame of a video and apply some kind of Pix-to-Pix or like image-to-image translation on them. You end up with this kind of like flickering effect because these diffusion models aren't very repeatable, right? It's like you give it a slightly different image and there will be whole sections of the image that change. In this work, we propose Pix-to-Pix 0, an image-to-image translation model that can preserve the content of the original image without manual prompting. We first automatically discover editing directions that reflect desired edits in the text embedding space. Okay. So I wonder what they mean by directions here. To preserve the general content structure after editing, we further propose cross-attention guidance, which aims to retain the cross-attention maps of the input image. Okay, so they're going to be doing some additional kind of stuff with the attention maps within the actual model here. So they're teasing a couple different interesting things here. We'll see how much they actually change the model architecture, whether this is more of a glue. Our method does not need additional training for these edits and can directly use the existing pre-trained text-to-image diffusion model. We conduct extensive experiments and show that our method outperforms existing and concurrent works for both real and synthetic image editing. Okay, I don't know what the benchmarks are, but they outperform them. Okay, introduction. I think they're gonna kind of talk about text-to-image diffusion. Everybody knows DALL-E, image gen, stable diffusion, of course. Images do not naturally come with text descriptions. Okay. Even with the initial and target text prompts, existing text-to-image models tend to synthesize completely new content that fails to follow the layout, shape, and object pose of the input image. Yeah, the composition of the scene in the image is very difficult to engineer with a prompt. Editing the text prompt only tells us what we want to change, but does not convey what you intend to preserve. Users may want to perform all kinds of edits on a diverse set of real images, so we do not want to fine-tune a large model for each image and edit type due to its prohibitive cost. Yeah, I mean, this extends just beyond kind of image editing and image diffusion models. I think as the models have gotten bigger and bigger over time, the realistic or the cost of fine-tuning is just going to get more and more prohibitive, and I think you're going to see more and more approaches that try to avoid fine-tuning as much as possible. Not just in image, but again, also in like text and LLMs. This idea of pre-training and fine-tuning, which was kind of the paradigm for deep learning for many years at this point, I think is going to go away, because when you're trying to create these user products, fine-tuning can't really be a part of that because it's just too expensive. To overcome the above issues, we introduced Pix2Pix0, diffusion-based image-to-image translation that is training-free and prompt-free. There you go. Here's first name it right there. A user only need to specify the edit direction in the force of source domain to target domain on the fly without manually creating text prompts for the image. Our model can directly use pre-trained text-to-image diffusion models without additional training. They're really selling on this no additional training required. An efficient automatic editing direction discovery mechanism without input text prompting. Yeah, so we don't know exactly what they mean by editing direction here. Let's see. Generic editing direction. Given an original word and an edited word, we generate two groups of sentences containing the original and edited words separately. Okay, so some kind of augmentation, prompt augmentation, which we've seen in some papers before. Then we compute the clip embedding direction between the two groups. Okay, here you go. This is what they mean by direction. The direction that they mean is the vector in clip embedding space. As this editing direction is based on multiple sentences, it is more robust than just finding the direction only between the original and the edited words. Okay. That's the key. That's another key sentence there. So you have a word such as cat and dog, right? You can feed that word token, the cat token and the dog word token into clip, and you'll get a point in the clip embedding space. And you could just take the vector between those, and that would be a direction in clip embedding space. But what they're saying here is that if you kind of generate some sentences such as a cat in a tree and a dog in a tree, and then you feed each of those two sentences into clip, those will also produce a point in clip embedding space, and you can also take a direction between those two. And the more of these sentences that are basically the same except for the word cat and the word dog, right? The more of those sentence pairs that you have, the better your clip embedding direction is going to be. So you could think of it almost as a form of data augmentation for individual words. This step only takes about 5 seconds and can be pre-computed. Okay, so generating all these prompt variants, and computing the clip embeddings for them takes about 5 seconds. Content preservation via cross-attention guidance. This is the second part of their novel contributions. Our observation is the cross-attention map corresponds to the structure of the generated object. To preserve the original structure, we encourage the text-image cross-attention map to be consistent before and after translation. Hence, we apply the cross-attention guidance to enforce this consistency throughout the diffusion process. We show various editing results while preserving the structure of the input images. Okay, so I don't know if they're necessarily using a transformer-based model, but whenever you're feeding images into a transformer model, you're usually cutting it up into image patches, and the image patches roughly act as a way of describing a specific part of the image, right? So your attention map, because the image patches are constrained to a specific geographic location in the image, they should be consistent if the scene layout is consistent, right? If we took this image of this dog with the glasses and we cut it into a 4x4 image patches, so there's 4 different image patches, you would expect the top left image patch and the top left image patch here to be consistent. I don't know if they're actually using a transformer though, so let's kind of wait to see exactly what they mean here by the cross attention map, whether it's an actual transformer attention map or whether it's a different model architecture artifact. Further improve our results and inference speed with a suite of techniques, autocorrelation regularization. Okay, so have some special type of regularization here. When applying inversion via DDIM, we observe that DDIM inversion is prone to make the intermediate predicted noise less Gaussian, which introduces the editability of an inverted image. Okay. Prone to make the intermediate predicted noise less Gaussian. So again, when what a diffusion model is doing is it's learning to basically add and remove noise. What you're doing is you're taking, basically starting with noise and then progressively removing noise over time, or if you're training, you're starting with the image and then adding noise over time. So largely what a diffusion model is learning, it's learning how to remove noise from an image. And the word intermediate here refers to the fact that the noise removing and noise adding process is not a single shot. It's usually multiple steps over time. So what they're trying to determine here is, or what they're kind of saying here is that the intermediate noise that gets predicted, I guess normally should be a Gaussian, but this inversion process is prone to making it not a Gaussian. Okay, hence we introduce an autocorrelation regularization to ensure noise to be close to Gaussian during inversion. Okay, then they also have conditional GAN distillation. Diffusion models are slow due to the multi-step inference. So this is the multi-step noise removal. To enable interactive editing, we distill the diffusion model into a fast conditional GAN model. Okay, this is kind of interesting. So rather than actually using the final diffusion model when they are performing inference, right, in production, the actual users doing this or using this model, they don't use the diffusion model. They're using a GAN model that has been distilled from the diffusion model. And distilling here means when you take one model and then you take a second model. So sometimes the first model is called the teacher and then the second model is called the student. And the student model tries to basically mimic the teacher model. So for any input that the teacher model receives, the teacher model produces an output. The student model will receive the same input, and the output of the teacher model would be used as basically the loss for the student model. So the student tries to basically match the teacher model, and this is called distillation sometimes. So they have a fast conditional GAN model that is basically trying to copy the diffusion model. and this allows them to create, or this allows people to use this image, or this whatever zero shot pix to pix image, pix to pix 0, without having to wait for multiple diffusion steps to happen, right? You don't need this multi-step inference anymore, which is characteristic of diffusion models. You basically now have a GAN model which just works on a single inference step. This is kind of cool. I don't know if I've seen that before, using diffusion model to distill it down into a GAN model. I wonder if they got that from somewhere, or if that is original to this work. We demonstrate our method on a wide range of image-to-image translation tasks, such as changing the foreground, modifying the object, and changing the style of the input for both real images and synthetic images. Extensive experiments show that pix-to-pix 0 outperforms existing and concurrent works regarding photorealism and content preservation. Extensive ablation study, and then they also post the code. So this is a nice little github.io. More examples. You can hover over. Very nicely done. In today's very competitive research world, having a nice set of images to show and a very responsive, interactive web page is important. And here's the actual GitHub. 100% Python. MIT license. Good to see. All right, let's go back to the paper here. For that, let's take a little sip of our highly caffeinated yerba mate. With generative modeling, image editing techniques have enabled users to express their goals in different ways. One line of work is to train conditional GANs that translate an input image from one domain to a target domain. So here you have the conditional GAN, but I don't think this is the actual distillation part. This is just the conditional GAN. So these are all probably slightly older papers that are GAN specific. Another category of editing approaches is manipulating the latent spaces of GANs via image inverting. Yeah, so this is older stuff too now, by the way. GAN latent space manipulation. There's definitely going to be a good picture for this, but yeah, I remember this was popular with celebrities, but none of these images are necessarily good. This one is kind of interesting to look at, right? So in a GAN, you have a generator and then a discriminator. So usually the way that you can think about this in your head is it's kind of like a bottleneck type of network, where the generator takes an image and then basically compresses it down into a smaller dimensional vector called a latent, right? Which is also a point in some embedding space. And the discriminator takes this and then basically reconstructs an image. So it takes this small little vector and then it reconstructs the actual image. So within this lower dimensional latent space, there are specific directions that you can move, right? If you have, for example here, celebrity, there's some distance in latent, like if you put every single one of these images in through the generator of a GAN, you would get a latent vector. And if you put every single one of these images through the generator in a GAN, you would get a different latent vector. If you took the difference in the latent vectors between all of these, you would find that there is some consistent direction, some consistent vector that basically moves you from smiling woman to neutral woman. They're not going to be perfect every time, right? The latent space of a GAN is not like theoretically optimal, right? It's not like the vector is going to be exact from here to here and here to here. But because that direction, right, between this latent the latent vector for this image and the latent vector for this image is going to be somewhat consistent for the concept of smiling to neutral, you could then simply take an image of a neutral man, right, and then add that direction, and you'd get a smiling man, right? So this kind of like latent space math actually works. And there was a time where people thought that kind of this was the future of image generation and image editing, and there was a lot of different work where people would train GANs in a special way such that the latent space is kind of disentangled or has like special properties. It's nicely shaped. But with diffusion models, I feel like the community has gone away from GANs, and GANs have kind of fallen out of favor. So all these different tricks and variants of GANs that people came up with over the years have kind of just fallen off to the wayside. All right, back to the paper here. They first project the target image to the latent space of the pre-trained GAN model, and then edit the image by manipulating the latent code along directions corresponding to disentangled attributes. Okay, so this is basically a better way of describing what I just tried to describe there with those Google images. Numerous prior works propose to fine-tune the GAN model to better match the input image, explore different latent spaces, invert into multiple layers, and utilize latent editing directions. Yeah, so there's a lot of stuff that people have done with GANs. While these methods are successful on single category curated datasets, they struggle to obtain high quality inversion on more complex images. I think this is a good critique. I think that when you look at a lot of the GAN work, a lot of it was always very domain specific, right? Like, for example, it would be these kind of celebrity datasets where every single image in this dataset is like a cropped image of someone's face, right? And with that type of data distribution, you can have certain freedom because there's so much consistency in that data set, right? It's only a single category. It's really only a single type of object. The variance in that data set distribution is actually very low. But for something like this, right, the variance in this kind of data set is significantly higher, right? You have everything from like a drawing of a 3D zebra to like a oil painting like this. The variance in this kind of image distribution is significantly higher. So the latent space that a GAN would create for this type of high variance image distribution would be very noisy, very difficult to use. So many of these kind of older GAN techniques would not work on such a diverse image data set. Text-to-image models. Recently, large-scale text-to-image models have dramatically improved the image quality and diversity by training on internet-scale text-image datasets. Yeah, I would say this is actually the biggest reason we've seen jumps in performance over the past couple years. However, they provide limited control over the generation process outside the text input. Editing real images by changing words in the input sentence is not reliable, as it often changes way too much of the image in unexpected ways. Some methods use additional masks to constrain where the edits are applied. Unlike these approaches, our method retrains or retains the input structure without any spatial mask. Yeah, this is the impressive part, right? Where in these images, they kind of largely stay the same, right? It's like you really do get a very clean edit from cat to dog, right? Like a lot of the background stays exactly the same. There is still some change. Like for example, here when you go from cat to dog, the width of the shoulders changes. So some of it is still not super precise, but say pretty precise. Other recent concurrent work. So here's some other works that try to do similar things. Learn condition diffusion models tailored for image-to-image translation tasks. Conditional diffusion models is basically just a diffusion model that is conditioned on something. So let's see if we have a nice picture. Yeah, here in this picture, I think C is the condition vector. text embedding C. Yeah, so this is when you have a neural net model, you can take the input and produce some output. But you can also take the input and you can take any additional information that you want, right? And when you do that, you can say that the model is conditioned on that additional information. So there's no limit to what you can condition a diffusion model on. You can condition it on text. You can condition it on some other latent or embedding vector. You can condition it on a category. It's whatever you want. So all these different works, they're going to have all these different types of things that they condition their diffusion models on. Image editing with diffusion models. Several recent works have adopted diffusion models for image editing. SD-Edit performs editing by first adding noise to the input image and then denoising it to increase its realism. Okay, so this one here, what it does is it'll add the noise and then denoise it again. So it's basically going, diffusion models add noise over a series of steps. So this is basically taking it a step backwards and then taking it a step forwards. Seems like a kind of, oh, seems bad for other reasons. It's later used with text-to-image models such as Glide and Stable Diffusion to perform text-based image painting and editing. Would have been proposed by incorporating. Okay, Imagic and prompt-to-prompt. I think we actually reviewed this paper. I don't quite recall anymore. Imagic requires great editing results, but requires fine-tuning the entire model for each image. Yeah, this is the annoying part, right? The bigger your model, the more expensive fine-tuning is. And it gets to a point where if your model is like huge, no one can actually fine-tune it because no one has a GPU big enough to fine-tune it, right? So, especially as these models get bigger over time, the appetite for fine-tuning is going to heavily decrease. Prompt-to-prompt does not require fine-tuning and uses the cross-attention map. Okay. Our work differs in 3 ways. Our method requires no text prompting for the input image. Our approach is more robust as we do not directly use the cross-attention map of the original text. Our guidance-based method ensures the cross-attention map of edited images remains close but still has the flexibility to change according to the edited text. Our method is tailored for real images while still being effective for synthetic ones. We show that our method outperforms SD-Edit and prompt-to-prompt regarding image quality and content preservation. I wonder how they actually measure this. If they're about to do a Frichet inception distance for this, I'm gonna punch the monitor. We propose to edit an input image along an edit direction. Okay, so here they're defining the edit direction cat to dog. There's probably going to be a mathematical symbol for this. We first invert the input x. All right, we're taking out our green, which is our mathematical symbol highlight color. So you have some input x tilde. To the corresponding noise map. Present a method for automatically discovering and pre-computing edit directions in text embedding space. Applying the edit direction naively often results in unwanted changes. Yeah, so this is the extra. Actually, here, this is exactly what they're doing here. This is a perfect figure. Perfect timing on figure 2. Given the source of a target text, we generate a large bank of diverse sentences using GPT-3. Okay, so that's interesting. They're using GPT-3 to actually generate these. We compute their clip embeddings and take the mean difference to obtain the edit direction. So, as a user, the only thing you specify is cat and dog. But the vector between cat and dog in clip space is actually going to be noisy, right? The way that they say it is that edit direction, right? The difference in clip space between cat and dog is going to result in unwanted changes. So instead, what you're going to do is you're going to basically create a bunch of sentences. A cat washes itself, a cat watching birds in a window, a cat licking its paw, this is my dog, a dog patiently waiting, a dog panting after a walk. You're going to feed each of these sentences into clip, and then you're going to get the difference between them. So this is the interesting thing here is I thought the sentences would be one-to-one. I thought it would be a cat washes itself, and then a dog washes itself. But that is not the case. These are different sentences. A dog waiting patiently for a treat, a cat watching birds in a window. So there's some funky stuff going on here, right? Because if the sentences are not the same, that means that there's additional kind of concepts leaking into the clip, right? So clip turns sentences into a vector. So all this other stuff, right? Treat, for example, here, and window, and birds, right? Those are going to impact the vectors that come out here of clip, come out here from clip. So it's interesting that you get a cleaner edit direction by having these additional concepts that are related to the original word cat. And those concepts that are related to the original word cat are chosen by GPT-3. So within GPT-3, there's a set of kind of words that are more similar to cat than they are to dog, and thus have a higher probability of being generated when you're generating a sentence. So this is very black box. It's kind of crazy that this works and they end up going with this. Wonder if it's like, right, it seems to me like they should have just come up with sentences that are basically identical except for the noun. But this is crazy. Crazy in a good way. Crazy in the way that it's crazy that it works, and kind of cool. To obtain edit direction, here you go. Here's the actual delta C edit is going to be the edit direction. To address this issue, we propose cross-attention guidance that guides the diffusion sampling process and helps retain the input image structure. Second. Note that our method is applicable to different text-to-image models, but for this paper we use Stable Diffusion, which encodes input image x tilde. Okay, so here's your image, and this image is part, this little sign here means that it's part of the real numbers of dimensionality x by 3. So images have some width and they have some height, and then they have 3 channels because they're a RGB image, right? Red, green, blue. There's 3 different pixel values for each pixel. So x and x here means that the width and the height of the image is the same, and actually they tell you right here, this is the images are 512 by 512. So first thing they do is they take that input image and then turn it into a latent code. So basically, it's just a small version of the image, but you're going to lose all the context, right? It's now just in latent space. So as a human, you can't look at this latent space and know what's going on. It's just going to look like a bunch of noise. But this latent space, you can see how it has an additional channel. It's now S by 4, so it's a little bit deeper, but it has a lower width and height, right? We went from a width and height of 512 to 64. So the overall size of this latent code is smaller than the overall size of this input image. And one thing that you see in these diffusion papers a lot is like a trick that people use is they'll perform the diffusion, right? They'll perform the removal and addition of noise on these latent codes rather than the original image. Because these latent codes are smaller, so adding and removing noise from a smaller dimensional tensor is more computationally efficient than adding and removing noise from a higher dimensional tensor. Okay. The inversion and editing described in this section happen in latent space. Here you go. So they are doing latent space stuff in order to make this all faster. To invert the text condition model, we generate an initial text prompt C. Okay. Using blip to describe the input image X. So what is blip? Blip, so blip is a 2022 paper. Here we go. We propose blip, a new VLP, vision language pre-training framework which transfers flexibility, blah, blah, blah. Okay, so vision language pre-training is very similar to clip, right? This here. So it's basically these big models that have been trained on both large images and large text at the same time, usually through some kind of contrastive loss, but there's other ways to kind of train them. So basically you can think of blip as basically a big model which has both vision and language understanding. So it kind of has some tangled latent space that is trying to represent images and text in the same space. So, I mean, that's just my assumption. I don't know 100% exactly if that's what blip is, but I'm guessing that's what it is. Inverting the real images, section 3.1. Deterministic inversion. Inversion entails finding a noise map. Okay, here we go, noise map, X inversion. Oh. Finding a noise map, X inv, that reconstructs the input latent code X naught upon sampling. In DDPM, this corresponds to the fixed forward noising process, followed by denoising with the reverse process. So this is effectively what diffusion models are doing, right? Is they have some forward noising process where they're adding noise, and then they have a denoising process where they remove the noise. And the model is learning what that noise is, right? It's learning how to denoise things. However, both the forward and reverse process of DDPM are stochastic and do not result in a faithful reconstruction. So stochastic here basically just means there's some randomness. Instead, we adopt the deterministic reverse process. Okay, so because they don't want that randomness, right? Because in this paper, they really want this kind of consistency. They're going to try to make this noising and denoising as not random as possible. So they have here the equation for their reverse process. So x t plus 1 is, x is the latent code. So you can think of it like the image. X with the tilde on it is the actual image. X without the tilde is the latent, which is basically just the image, but it turned into like a smaller version of it that looks a little bit like noise, right? So here, the subscript here, t, is going to refer to the time step, right? So this noising and denoising, there's going to be t total steps of that noising and denoising. You're going to go from x0 to x1 to x2 all the way to xt. So going from x0 to x1, you're going to take x0, you're going to feed it here, right? x0, x0. T is going to be 0. T is going to be 0. C is the condition, right? Encoded text feature C, which is basically your conditioning. What are you conditioning on? So remember here when we were talking about that diffusion models, you can condition them on anything. here they're going to be conditioning it on a text prompt, so some text that is turned into another type of vector. And then you have f sub theta, which is going to be a neural net. This is actually the actual diffusion model here, right? F sub theta predicts the final denoise latent code. And then this little epsilon theta here is the actual denoiser. Okay, so actually this is the net that predicts the noise. Epsilon theta is a UNet-based denoiser that predicts added noise in x sub t, conditional on time step t and encoded text features c. So this is a little neural net here. It takes your current latent code or image, right? It conditions it on the time step and then also on the this word vector here, which is basically a text prompt that has been generated with this blip model. And here you basically just have a noise scaling factor. So this like square root stuff here is just kind of a fancy way to regularize this stuff here. Ooh, sorry. Probably shouldn't be doing everything in green. But here you see square root of alpha bar t plus 1 and then square root of 1 minus alpha bar t plus 1. So all this is doing here is it's basically trading off between f theta and then epsilon theta here. And f theta x t t c is equal to... Okay, so this is not actually... F theta is just this. So there really is only one model here. It's this one here. This epsilon theta. This is the only model. This f sub theta, this function right here is merely just a function of this here. So really you could take this f sub theta and then plug in this equation here into here, and you'd get an equation that only depends on this alpha bar, xt, t, c, and this. So that's all that's going on here. Gradually add noise to the initial latent code x naught using DDIM process, and at the end of the inversion, the final noise latent code is assigned as xinv. So there's different types of noise that you can add. Sometimes these are called samplers, I think. And we did review a paper a while ago now, but it was a paper that actually went through and kind of looked at all the different types of like samplers and the different types of noise that you could add in these diffusion models. I don't really remember which one is kind of the best one to do, and I'm assuming that for this paper the authors just kind of chose either the most generic one or the kind of agreed upon best type of noise and sampling. The inverted noise maps generated by DDIM inversion. Okay, so these are noise maps. Oh. Oh. My highlighting is no good today. Right, so this is an actual model, right? The actual model generates noise, and that noise, right, has to be the same dimension as the latent code here, right? So the latent code x naught has dimensionality s by 4, and you're going to be adding and removing the noise to this latent code. So the noise map here has to be the same dimensionality, which is what you see here, right? The noise map is also s by 4. Okay, Gaussian white noise causing poor editability. A Gaussian noise map should have no correlation between any pair of random locations and 0 mean unit variance at each spatial location. Okay, which would be reflected in its autocorrelation function being a Kronecker delta function. So Kronecker delta function is a fancy way of describing a function that basically has 1 at a specific location and then 0 elsewhere. So it's kind of like a spike in a specific location. Let's see. Yeah, this is what it looks like. So it's basically 0, 0, 0, 0, 0, 0, 0, and then it gets to a specific point and it jumps up to 1 and then it goes back to 0. So basically the entire mass, right, all of the area under the curve is only at a single specific point. So what they're saying here is that a Gaussian noise map should have no correlation between any pair of random locations. Zero mean, unit variance. So zero mean means centered on 0. Unit variance means that the standard deviation of a Gaussian, right? A Gaussian, I feel like if you're watching this channel, you do know what a Gaussian looks like, but just in case. This is what a Gaussian is, right? Your standard bell curve, right? And the variance refers to the spreading of it. So here, the variance would be this sigma parameter, right? So here you have sigma, -2 sigma, -3 sigma. So a wider variance means that the Gaussian is wider. So like here, right? This blue is the mean, so this is 0, and then the variance is 0.2. This red line, the centered on Gaussian, 0 mean, and then the variance is 1. So this is unit variance. Here, this red one is 0 mean, unit variance. This gold line or yellow line here is 0 mean and then a larger variance. And then this green line is -2 mean and then not unit variance. So you can see here the difference between unit variance, not unit variance, and then the difference between 0 mean and a different type of mean. So here they're describing 0 mean, unit variance. So it's a well-shaped Gaussian looking curve at every point. And they say that because they don't want the noise to be correlated with each other, that the correlation function, right, like the noise's relation to other noise should basically be nothing. The noise should not have any relationship to any other kind of point in the image, and it should only be auto-correlated with itself. That's what that sentence there means. Following this, we guide the inversion process with an autocorrelation objective comprised of a pairwise term L pair and a KL divergence term LKL at individual pixel locations. So KL divergence, we've described this before on this channel, but basically it's a way to measure the, I don't want to use the word distance, but it's basically the similarity of two distributions, right? So, for example, the KL divergence of this red Gaussian and this gold Gaussian is probably smaller than the KL divergence of this red Gaussian and this green Gaussian or something like that. Maybe not, but because these are all so similar, but basically the KL divergence is how similar is one distribution to a different distribution. It's a little bit tricky of a term because it's not commutative, right? Like KL divergence of A and B is not the same as the KL divergence of B and A, and it's not quite a distance metric, and there's a little bit of complexity there, but in a machine learning research context, whenever you see KL divergence, it's largely just being used as a distance metric between two distributions. And here it's being used as a distance metric between the noise distributions. As densely sampling all pairs of locations is costly, we follow 29 and form a pyramid where the initial noise level, okay, so you have some noise level, I think that's eta, right? Let me double check that. Eta, Greek letter. Yeah. Script n is called eta. So eta naught has a dimensionality of 64 by 64 by 4, which I think is actually just s by s by 4, right? S is 64. Yeah, s is equal to 64, so the dimensionality of the noise level is the same dimensionality, right? S by 4. is the predicted noise map epsilon theta. I think sigma what is the like little like I keep calling this epsilon, but there's a part of me that thinks that it's actually not epsilon. Right, because epsilon, it actually looks like a backwards 3, but this one, these ones here, it's not that. It's like a kind of like a C with a line in it. I think it is epsilon, I just don't. Okay. Sigma 0, sigma theta for the epsilon, or epsilon theta for the predicted noise map. And each subsequent noise map is average pooled with a 2x2 neighborhood. Okay, so they're doing pooling here. So average pooling is kind of a way, you see this in convolutional neural nets a lot, where at the very last layer before you go from the convolutional feature maps into the fully connected neural net at the top of a convnet, you'll do these kind of pooling operations. And pooling is kind of, there's a lot of different types of pooling and it can get complicated, so I don't want to go too deep, but the TLDR for pooling is that you're basically reducing the dimensionality. You might, if you have 100 things, you pool them and you might reduce it to 25 things. So it's just a way of reducing the dimensionality, right? So it seems like here what they're reducing it to is 8x8. So they go from a 64x64 to an 8x8. Creating 4 noise maps. Okay, so first of all, this is going to be blue. And then here are your 4 noise maps. Okay, so I wonder what they're going to do with these 4 different noise maps. The pairwise regularization at pyramid level P. Okay, so the pyramid is... Where did they introduce the concept of the pyramid? Incidentally samples we follow and form a pyramid. Okay, so the actual latent code, right? This here, the latent code, x naught, which is s by s by 4, 64 by 64 by 4. It'd be very expensive to sample the noise at every single point in that. So they're going to be sampling at a subset of points. So they're doing this pyramid and then this pooling in order to basically you only use a subset of those points. Yes. Food station. Yes. Is the sum of the autocorrelation coefficients at possible delta offsets. Normalized over noise map sizes SP. So it seems like maybe the dimensionality of the noise map is going to change. I would assume S to just be the same as SP, but see what happens here. Okay, so here you have L pair. So generally when you see this L, it means a loss. So I assume this is going to be the loss function. So the loss function here is the sum over all P, right? P is the pyramid. Yeah, so pyramid level P. So you have some level P within the pyramid, and you're summing over all levels of the pyramid, right? So that's what this summation is. You're multiplying 1 over s squared P. So this is the noise map squared. So this might be the... Not a sellout, dude. the summation of delta to SP minus 1. So what is this? Okay, here's that is. We randomly sample a shift rather than only using, enabling us to propagate long term. So this is the Dirac delta, I think. So that's what that summation is. And then here, X, Y, C, this is going to be the X is the width, then the Y, and then the channel. So the dimensionality of all these latent codes in the original images, they're all 3 numbers, right? It's 64 by 64 by 4. Or if you go here, it's X by X by 3, S by S by 4, right? There's 3 numbers here. And those 3 numbers correspond to the X, the Y, and the channel. So that's what the summation here is. You have eta P, X, Y, C. So this is the, here we go, the initial noise level. So this is the noise level at that individual pixel, right? And not just the pixel, but like specific X, Y position and channel position at the pyramid level P. And then here you have the same noise level, but at a slightly different X location, right? So you see here how is X minus delta and then Y minus delta. So you're looking at the difference in noise levels between a point that's kind of immediately above and immediately below and immediately to the left and immediately to the right, right? So they're basically doing this very careful loss between the noise in, ideally they would do it for every single pixel, right? All pairs of locations is really what they would want to do. They would want to do it, the difference between every point, every pixel, and every other pixel. But that would just be outrageously expensive, right? If you come from a computer programming background, it's like, right, think about having a for loop and then a for loop in a for loop and then a for loop in a for loop. Like very quickly it gets out of control and you kind of end up with a huge amount of calculations that you need to do. So all this extra stuff here that they're doing with the pyramid and the 4 different levels of this pyramid and average pooling, all of that is basically just because they couldn't do this operation here for every single pixel. Indexes into spatial location using circular indexing and channel. I think circular indexing just means that you go, so 0 indexing, for example, is when you start at 0 in an array. Circular indexing, I think, means that it wraps around. So once you get to the final X position, it'll circle back around and it'll hit the 0 with X position. I think that's what that means. We introduce a few changes to the autocorrelation idea to boost its performance in the diffusion context. We randomly sample a shift at each iteration rather than only using delta 1 as in 29, enabling us to propagate long-range information more efficiently. So relying on multiple iterations to propagate long-range connections causes intermediate time steps to fall out of distribution. We find that enforcing the zero mean unit variance criteria strictly via normalization leads to divergence during the denoising process. Okay, interesting. So they want the noise, right? That they have this diffusion model, and it's adding noise and removing noise to the image over a series of time steps t. And they want the noise that gets added and removed, they want that to be as close as possible to a Gaussian with zero mean, unit variance, and no correlation between any pixel in the image, right? And one way you could actually do that is just normalize it. So at every point in this denoising and noising process, the noise that gets produced, you just normalize it so that you always have zero mean unit variance. And it seems like they probably did try to do that, but they ended up getting this kind of divergent behavior. So I wonder if they actually tried it and then it failed, or whether they just assumed that it would fail. It seems like they reference a paper here. Analyzing and improving the image quality of StyleGAN. Okay, yeah, so maybe they just read that paper and they decided to just follow the advice of that paper instead of trying it themselves. Instead, we formulate this softly as a loss KL as used in variational autoencoders. This enables us to softly balance between the two losses. Okay. So this is the KL divergence, right? The loss here that allows you to compare one distribution to a different distribution, and their final autocorrelation regularization is basically the combination of both of those. You have this L pair, which is the one that they had here, right? Where basically you're looking at the noise at every single pixel. And then you have the KL divergence. And then they have this extra hyperparameter lambda here that is tuned such that the KL divergence doesn't dominate the pair and the pair doesn't dominate that KL divergence. So this lambda here is chosen by the human. Discovering edit directions. Recent large generative models allow users to control the image synthesis by specifying a sentence that describes the output image. We instead want to provide the users with an interface where they only need to provide the desired change from the source domain to the target domain. We automatically compute the corresponding text embedding direction vector. So this is the vector in clip embedding space that goes from cat to dog. We generate a large bank of diverse sentences for both source and target, either using an off-the-shelf sentence generator like GPT-3 or by using predefined prompts around source and target. Okay, so actually maybe they do an ablation study about whether or not kind of having different sentences changes things. I would assume that it would. We then compute the mean difference between clip and the sentences. Edited images can be generated by adding the direction to the text prompt embedding. Okay. Figure 4 shows the result of several edits with directions computed using this approach. Where's figure 4? Here we go. We find text direction using multiple sentences more robust than a single word and demonstrate this in section 4. This method of computing edit directions only takes about 5 seconds and only needs to be pre-computed once. I mean, I think the 5 seconds is kind of an understatement because loading the clip model onto your GPU memory takes more than 5 seconds. So the final inference step probably takes 5 seconds, but loading the model and then unloading the model, like all the like extra stuff, like I don't know, spinning up the Docker container, all these different steps are going to take, they're probably longer than 5 seconds. Next, we incorporate the edit directions into our image-to-image translation method. Recent large-scale diffusion models incorporate conditioning by augmenting the denoising network. Okay, this is the actual diffusion model here with the cross-attention layer. We use the open source stable diffusion model built on latent diffusion models. Okay, so they're just basically using your vanilla stable diffusion, probably version 1.4. The model produces a text embedding C with clip. So clip is contrastive language image pre-training. It's basically just this text and image model, right, that's been trained with a contrastive loss to produce a latent space that both images and words or sentences can be projected into and has some semantic relationship between those, right? So an image of a dog and a sentence that contains the word dog should be somewhat close together in the clip latent space. Next, to condition the generation on text, the model computes cross-attention between encoded text and intermediate features of the denoiser. Okay, so this is the attention function. This is an actual transformer attention here. So in transformer is a type of deep learning architecture, right? It's like one little piece. I don't know what the right word is. It's like a repeatable block that gets used in a transformer, right? The attention block. And the input to attention blocks are these three different things here, usually called keys, queries, and values. K, Q, and V. This is just an extra softmax. That's also part of the attention head. So what are they doing here with these? So WQ is the weight matrix of Q, right? So this attention block has, just like any other deep learning layer, right? There's some weights and some biases that are persistent over time, and these are those weights and biases are what get changed with gradient descent and produce the different behavior, right? That's how deep learning models, what they're really doing is they have some set of internal parameters, which are normally called the weights, and those internal parameters get adjusted over time with gradient descent, and that's effectively what learning is. And at the end of training versus at the beginning of training, because of the values stored in those weights, you're going to have different behaviors. So inside an attention block, there's different weight matrices. There's one for the keys here, W key or WK. There's one for the queries, and then there's one for the actual values here, WV. Okay, are computed with learnt projections, W key. Okay, so they're calling it learned projections here, but it's basically just weights. You could think of it that way. On intermediate spatial features of the denoising unit. Okay, so what is this? What is intermediate spatial features? So X of T is the latent code, right? So it's the actual image. It's this image here. But this is the raw image. They turn it into a latent code, which is basically just, you could think of it like a smaller version of this image that it looks noisy and you can't interpret it as a human, but it's just basically a smaller version of that image. And then you have your actual diffusion model, which is this denoising UNet. And the diffusion model is conditioned on the text embedding, also the specific time step of the diffusion process. But in that diffusion process, right, as it's going and removing and adding the noise, there's going to be intermediate features within this model, right, this diffusion model. And it seems like that's what they're actually feeding into here, right? That's what they're putting into the queries. So what you're feeding into the keys, queries, and values of the attention head is going to is like, you have to pick specific things, right? And so here what they're interested in doing is they're interested in looking at the cross attention of basically this text embedding and then the features that come out of the diffusion model, but not the final ones, right? Because the diffusion model outputs just a full image or a full latent code. They want basically some of the intermediate features of that. So it looks like the queries, what they're putting in here is going to be these intermediate features, and then for the keys, it's going to be the latent or the text embedding. And then the value is also going to be the text embedding here. So the attention map is going to be over these intermediate spatial features and then the text embeddings. D is the dimension of projected keys and queries. Of particular interest is the cross-attention map M, which is observed to have a tight relation with the structure of the image. So originally I thought that what they were going to do is they were going to basically use a vision transformer and cut the image into patches, and then that's why the cross-attention map would have a high correlate, kind of be very tightly correlated with the structure of the image, because when you break up an image into its image patches for a vision transformer, you're basically preserving the spatial structure of the image. But in this particular attention map, the spatial structure of the image is preserved because the diffusion model has this thing here, this intermediate spatial features. These intermediate spatial features are in some way preserving the actual structure of the image. I wonder what the dimensionality of this is. Like, I want to know how they get these intermediate spatial features. Individual entries of the mask Mij represent the contribution of the jth text token towards the ith spatial location. Okay, so cross-attention map, they're calling it here mask, but this is the same thing. So this cross-attention map is going to have some dimensionality. Why is this doing that? And then each point in this cross-attention map, which, right, is just a matrix. It's a two-dimensional matrix with indices I and j. So the position ij corresponds to the jth text token and the ith spatial location. So basically you're getting this attention map, which loosely is telling you how much each token in a sentence is related to each individual part of the image. Cross-attention map is specific to a time step. Okay, so there's an additional complexity here that because the diffusion model is a multi-step process, you're going to have a different intermediate spatial feature at every time step, right? You see how there's a time dependence here. It's x sub t, which means that this attention map, which is calculated, right, with these q, k, and v matrices here, there's going to be a different one at each time step. So there's going to be t different attention maps M. To apply an edit, a naive way would be to apply our pre-computed edit direction delta edit to C, and then use C edit equals C plus C edit for the sampling process. Okay, so what they're saying here is that you could just take your text embedding, or your text embedding C. You could calculate the edit direction, right, which is this thing that they were doing here, where they were basically taking the cat and dog, creating a bunch of these sentences, and then getting the difference between these two sentences in clip space, and that gives you the edit direction. So they say, hey, well, you could just take that and then just add it, right? You could just say C edit equals C plus delta C edit, and then just see what you get. What they're saying is this approach succeeds in changing the image according to the edit, but fails to preserve the structure of the input image. So they really want most of the image to stay the same. And I can kind of see where they're going to start setting this up here, right? Where because this attention map allows them to represent the contribution of specific text tokens to specific spatial locations, they will be able to know which parts of the image to edit. And that's how they're going to preserve the structure of this image. Okay, the deviation of the cross-attention maps during the sampling process results in the deviation in the structure of the image. As such, we propose a new cross-attention guidance to encourage consistency in the cross-attention maps. Okay, so this is the second novel contribution of the paper that they introduced in the introduction. Or that they introduced in the introduction. What am I saying? But this is how they're going to basically add some kind of regularization, some kind of forcing function that's going to make sure that the images stay somewhat consistent, right? It's like really the achievement of this paper is that they can go from image to image, and most of the image stays the same, right? So you see here the cat turns into a dog, and it only really changes the face, right? So there's some cross-attention map here for this image, and the area of the image that corresponds to the flowers is going to have a very low attention with cat and dog, right? Like there's not a ton of relation between this flower and the cat and the flower and the dog. So that's why this part of the image doesn't change, right? Follow a two-step process. We reconstruct the image without applying the edit direction, just using the input C. And then we apply. Okay, so they're also doing this guidance weight. So this paper is complicated. There's a lot of different tricks that they're using here, right? So guidance weights are basically a way of being able to create kind of like a slider between two things. So basically what they're doing here is they're going to reconstruct the input text C. So they basically, they do it with a blank C, and then they do it with the C that they want, and then that allows you to edit. Very nice guidance weight fusion models. See if we can find a nice picture. No, we don't have any nice pictures of guidance weight. Like there's one picture. Just using the input text C to obtain reference cross-attention maps for each time step. Okay. These cross-attention maps correspond to the original image structure E, which we aim to preserve. Next, we apply the edit direction by using cedit to generate cross-attention maps medit_t. We then take a gradient step with xt towards the matching reference mref_t, reducing the cross-attention loss. They have a cross-attention loss here. XA is cross-attention, and XA is the L2 difference, so these two parallel bars here, right, that just means L2 difference between MT edit and MT reference. So this is the guidance part, right? So your MT edit is with the edit direction, and MT reference is without the edit. So basically the cross-attention map with only the text embedding, and then the cross-attention map with the text embedding and the edit direction applied to that. This loss encourages MT edit to not deviate from MT ref, applying edit while retaining the original structure. Okay, so here's the actual algorithm. So this is kind of pseudocode, and this here is written obviously in math or LaTeX, right, is the actual way that they would write this. LaTeX is a way of writing math equations like this into a PDF. But there's going to be actual Python code here in their GitHub repo that basically implements that. So this is the same as this, right? It's basically just pseudocode. All right, so let's see what they have. XT, same as XInv. Noise regularized DDIM inversion of latent code corresponding to X. Okay, so this is the latent code of the image. So this is the image, and then this is basically the image, but fed once through this diffusion model such that it's like a little noise vector, or a little smaller version of the image. You could think of it that way. You have your context, or your text embedding C. You have delta C edit, which is the direction of the edit in clip embedding space. Right, it's a vector that has the same dimensionality as C, and you could add C to C edit. And then you have this lambda XA cross attention guidance weight. So, yeah, this is not ideal. So they have a lambda XA here, and then they have a lambda here. These are two different terms, very completely different. So the lambda here is used to basically ensure that the noise is not correlated, and the lambda here is actually used to basically trade off between the attention map of the image with the edit direction applied and without the edit direction applied. So kind of unfortunate that they used lambda for both of those. Those are not related at all. Okay, so that's the things that are going in, and then the things that are going out of this algorithm. So you could think of it like this is the, you think of it in Python terms, right? There's some input to a function, and then there's an output to the function. So here, this is the input, and then this is the output. Okay, so first thing they do is they compute the reference cross-attention maps. So for each step in the diffusion process, and here they're going backwards, they're going from time step capital T all the way back to time step 1. Here's the noise. Here's the cross-attention map. This is coming from the actual diffusion model, which is, again, conditioned on the time step, but also the C, the actual input text. Update xt. So here, this update, I think it's just literally adding it. So basically, you're just going to take this, the current latent code, and then just add the noise that you calculated from your diffusion model, and then you're going to get the xt minus 1, which is going to be the latent code with extra noise on it, or noise removed. One of those two. Edit with cross-attention guidance. So now they're basically going to do something very similar, instead of conditioning here, you have the same diffusion model as here, right? You see this? It's the same thing, except rather than conditioning on just C, which is the input text features, they're now going to be conditioning on C edit, which is C plus the edit direction. But then everything else is basically very, very similar, right? Here, this is the L2 loss of medit T with mref T. So here you have mt ref, which is basically, right, the cross attention map calculated with only the text input text. And then you have the cross attention map calculated with the input text that has been added with the edit direction. So this basically here is where the guidance weight comes into, this guidance weight here, cross-attention guidance weight, comes into play. You're going to basically take the L2 difference between those, and then you're going to, you add, this is where it comes in here. You're taking the latent code, and you're subtracting this delta. Right, so this is where actually all the magic happens here. Right? All the magic is happening here, where you're basically changing this latent code in a direction that is moving everything in the direction of your delta C edit. So like, at the end of the day, there's a lot of different steps here, and it feels like it's confusing, but all it's really doing is it's basically taking this vector direction in clip embedding space that you get from these sentences, and then averaging all the direction of these sentences to each other. And you're applying that edit direction to the latent code of the image, and then you're basically just you're just doing denoising. So it's basically a diffusion model that you're modifying it's a diffusion model in latent space, and then you're modifying those latents with these edit directions. And then there's all this kind of extra crap that you're doing just to make sure that those edit directions are nice and clean, and that you have kind of a good trade-off between not a good trade-off, but like you have attention maps that are correct, right? Okay, update current state xt with noise prediction epsilon hat. Okay. Oh, okay, this is the actual function. The update function is Yeah, it's not just like a vanilla add. So like it's not like they're just taking the latent code and then just adding the noise. There's this kind of additional like alpha term here that they have to add. I feel like they could have just taken this equation here and just put it here. Like here they split it into two equations for no reason, right? They introduced this like f sub theta here. When really they should have just taken this part here and then just put it right there, which is exactly what they did here, right? I think this is cleaner, and then you don't have this extra f sub theta, which can be confusing. Okay. Damn, guys, this is slow. Yeah, already an hour 25. All right, let's maybe start to speed up here a little bit. Experiments. Our image-to-image translation method can be used to edit real images. We demonstrate our methods on Stable Diffusion 1.4. We perform qualitative evaluations using 4 image-to-image translation. Okay, so here are different translations. They have cat-dog. They have horse-zebra. They have cat to cat with glasses, and then they have sketch to oil pastel. All input images are taken from the Leon 5B dataset. Okay, so this is the actual dataset that they're using. Horse to goat, cake to chocolate cake, dog to cat. Look at these. These are pretty good. Cat to yawning cat. These are quite impressive. Interesting how when you go from dog to husky, it gets rid of this like bokeh effect. Right, and for example here, going from dog to jumping dog, it makes this strip here white. So you see how here it's like 2 yellow strips, and then here it goes to yellow and white. So like there's still a little bit of weirdness going on where it's not 100% changed. SD edit with word swap, prompt to prompt, GDIM with word swap, Rs. Okay, so these are probably the, these are going to be the different things they compare it to. So SD edit is a different type of, it's this stable diffusion edit. It's like a different paper where people use a different approach. So you can see how SD edit like changes the actual structure of the image. We observe SD edit and DDIM plus word swap show deviations in structure, while prompt to prompt struggles to perform the edit. Our method shown in the last column successfully applies the edit. So prompt to prompt doesn't actually do anything. And then SD edit and DDIM, both of these, they do things, but they kind of like change the structure of the image. Okay. For quantitative, we measure 3 criteria: whether the edit was applied successfully, whether the structure of the input image is retained, and if the background regions of the image stay unchanged. So this is all subjective. There's nothing quantitative about this. We measure the extent of the edit applied with clip accuracy. Yeah, this is not necessarily a great quantitative metric. Basically what they're referring to here is you feed both of the images into clip and then look at the distance in clip embedding space between those 2 images and use that as a kind of a proxy for how similar these images are. And people used to do this too with, for example, VGG was another one, or AlexNet, where they would basically feed images into a ConvNet and then look at the difference in the final layer and then use that as a distance metric between images. But there's a lot of things that can go wrong there, and it's, I don't know about wrong, just it's kind of a noisy signal is maybe a better way of saying it. So okay, the structured consistency is measured using structured dist. So this is some other structured distance metric. Lower score on structured dist means that the structure of the edited image is more similar to the input image. And then finally, they have another one here, background LPIPs. Measuring the LPIPs distance between the background regions of the original and edited images. Background regions are identified using the object detector DETIC. Okay, so they have some object detector which masks out the background, and then they feed both of those backgrounds into this LPIPs error, and then that gives them some quantitative number that tells you how similar the backgrounds are. So, I mean, I'm not in love with these. I think these kind of like manufactured, engineered quantitative metrics they have all kinds of issues, but I guess it's better than nothing. Qualitative shows various edits applied. For each result, we show pairs of images. Okay. In this section, we compare our approach to some previous and concurrent diffusion-based image editing methods. All the approaches use stable diffusion with the same number of sampling steps and the same classifier-free guidance. So they're comparing to SDEdit. Okay, so what is SDEdit really doing? It's adding stochastic noise and then subsequently denoises. So SDEdit, basically, it's a much simpler technique. According to this description, all it's really doing is it's going backwards in time in the diffusion process and then re-rolling. So it basically like undoes it's like undoing some of the diffusion and then redoing it, conditioned on the new text prompt. And then prompt to prompt swaps the source word with the target and then uses the original as a hard constraint. So this seems like a more constrained version of the current approach. Maybe it doesn't have as much of the interesting stuff. And then this final one that they're comparing it to here, DDIM plus word swap. We invert the deterministic for DDIM process and perform sampling with edited prompt generated by swapping the source with the target. Okay, so basically it's the same thing as this one here, the SDEdit, where they just kind of swap the words. We compare our approach with the baselines. Both SDEdit and DDIM plus word swap methods struggle to retain the structure, and they do not use the cross-attention map. We compare our method against the baselines and see a similar trend. SDEdit and DDIM plus word swap struggle to retain the structure. On the other hand, prompt to prompt gets better, and background error, blah, blah, blah. Okay, I mean, they're just reading into these like distance metrics that are kind of bogus anyways. Ablation study. We ablate each component of our method. I think this is kind of more important. This method has so many different steps and so many little things that you kind of want to be able to see the ablation study here. Like, how important is having all this crap that they introduced, right? All these different tension masks or tension maps and like the clip and then the blip and all this stuff, right? It's like, I want to know how much of this is actually doing something and how much of it is just unnecessary over-engineering. Config A does not retain structure. Okay, config B replaces, proves both the structure. Config C adds the core autocorrelation regularization when performing the DDIM inversion, and config D replaces the word swapping with our sentence-based edit directions. Both of these changes cause the desired edit to get applied more consistently, reflected by the improvement in clip accuracy. Finally, config E adds the cross-attention guidance and corresponds to our final proposed method. Okay. Comparison. Compare method to several prior diffusion-based image editing methods. Okay, so these are just the weird metrics though, so like, what does it mean to go from 69% to 71% on clip AC? I don't know. What does it mean to go from 0.28 to 0.26 to 0.19 on LPIPs, on background LPIPs? Difficult to say. Okay. With guidance, without guidance. So I think the guidance here is the attention map stuff. So you can see here how in this kind of ablation here, they do it with a cross-attention guidance and then without cross-attention guidance. So you can see here how the cross-attention guidance is very important at preserving the image structure. This one is actually, this is the best example here, I think. Like, go from horse and you're trying to go to zebra. If you have the attention guidance, see how the image structure is largely preserved. You're losing a little bit, right? You're losing the door here. But when you don't have it, it just loses it completely. Okay, when cross-attention guidance is removed, the edited image does not adhere to the input structure. Okay, so the cross-attention guidance is critical. You do need it. Model acceleration with conditional GANs. One of the shortcomings of diffusion-based methods is that both inversion and sampling require many steps. To circumvent this and to train a fast image-to-image translation model, we can generate a paired dataset of input and edited images and train a paired image conditional GAN. Yeah, so this is the distillation that they're doing, where they're going to take all this stuff that they just did, right? This diffusion model with the cross-attention maps, guidance weights, the clip model that takes the cat and dog and creates those sentences, and then you get the edit direction and clip space. And they're going to try to take this giant pipeline and compress it into one single inference step. And they're going to do that by trying to distill the model into a GAN. So the GAN they're going to pick here is called CoMod GAN. They're going to be training this on an NVIDIA A100 with PyTorch. So this is a big boy GPU. It's a $10,000 GPU right there. The distilled model only takes 0.18 seconds per image, reducing inference time by a factor of 38,000 times. Yeah. This is like low-key, like the most impressive part of the paper for me. Like, I really wonder, like, did they come up with this themselves? Because, like, this idea of, like, distilling a diffusion model into a GAN in order to drastically improve inference speed, that's very cool. That's a very original idea. You know, and it seems like we read a bunch of papers where people were trying to reduce the total amount of diffusion steps, and they were trying to do all this crap with the diffusion model itself in order to make it faster, but here's a way to do it that's significantly faster and actually quite simple to understand. Model acceleration with conditional GANs. We show the result on the original diffusion model and conditional GANs. So this is with the actual pipeline, so with the actual diffusion model. And then this is with the GAN that has been distilled. So you can see how it's not exactly the same, right? At the end of the day, when you're distilling a model from a teacher into a student model, it's not going to be exactly the same. Usually the student model is going to have much less parameters than the actual parent or teacher model. In this case, it might be about the same. I'm not 100% sure. What makes the diffusion model slow is that they have to perform multiple inference steps. It's not that they have more parameters. So maybe the GAN actually has more parameters than the diffusion model. But you can see how it kind of changes it a little bit. But maybe not even necessarily for the worst. It kind of seems like the GAN actually does quite well. Okay, we construct an ablation study where we add different components one at a time and observe the effects. Okay, so here you see This is the DDIM with the L auto, and then the sentence directions with LXA. This is the cross attention loss. So this is the full Monty. This is like every single thing that they described. This is not with the GAN, so just FYI, this is only the diffusion model. This is they're taking away different parts of that diffusion model pipeline. So here, instead of the sentence directions, they're basically just swapping the words in the prompt. So you can tell how going from the word swap to the sentence directions is actually kind of the biggest jump here, right? And then here you have different diffusion models, DDPM, DDIM. Here you have the addition of the auto loss, which I think is, what is the auto loss? Okay, the auto loss is the combination. Is this like making sure that the noise is independent? Yeah, it really seems like the big step here is the word swap to sentence direction. Limitations and discussion. We propose an image-to-image translation method to perform structure preserving image editing using a pre-trained text-to-image diffusion model. We introduced an automatic way to learn edit directions in the text embedding space. We also propose cross-attention map guidance to preserve the structure of the original image after applying the learned edit direction. This is, I think, the coolest part, and then the GAN part is also really cool. Limitations. The resolution for the cross-attention map is 64 by 64. Yeah, so I mean, if you had higher resolution images, higher resolution latent maps, maybe you could do this entire approach on the image directly and not have to do it on the latent version of the image. I wonder if that would work. Although our approach can work with the resolution of any cross-attention map, if the base model has a higher resolution, then our approach can also provide even finer structure guidance control. Okay, and then they thank a bunch of people. Adobe internship. Quite cool. We're almost at the 2-hour mark here, so probably just going to end it there, but that was an interesting paper. My general thought is that it's a little bit over-engineered. There's a lot of complexity here. I still am not 100% sure whether... I feel like the fact that GPT-3 is generating these sentences rather than these sentences just being kind of replaced, I feel like there's probably some weird effects here, right? Where like dog and related things, like if you had an image that was like a cat next to like a cat toy and you did cat to dog, it might turn the dog or the cat toy into a dog toy, right? Because it's like the way these sentences work and this edit direction is going to work. It's like anything that's dog related and anything that's cat related is going to like move more towards like a dog related version of it. So like maybe that's intended. I'm not 100% sure, but like I feel like there's weird dynamics here that you get by having GPT-3 generate these. I do like this kind of general approach of kind of using getting the edit direction in clip space by using a bank of sentences rather than a single sentence or the actual difference between cat and dog. And what else? I thought that the conditional GAN distillation was really cool. I thought that was a really great idea. I don't know if we've seen that before. I don't know if it's original to this paper. It seems too basic to be original. It seems like somebody would have come up with that before. But if not, this is like the IMO, like the most important part of this paper is this like random little throwaway thing at the end. But yeah, cool work coming out of Adobe Research. Adobe, of course, very famous for their Adobe Suite, which is popular for kind of creative professionals. So I guess look forward to seeing this kind of capability in the Adobe Creative Suite. But this was all done with Stable Diffusion, and of course this is published work, so you can probably see this in Stable Diffusion and Midjourney and all those other kind of like image companies. They'll probably have some version of this as well. Cool. Thanks for listening. Make sure to like and subscribe, and yeah, look forward to more content this week. I'm going to be trying to do some short form vertical content, and going to be continuing to step up my thumbnail game. So, guys, later.